So the first announcement for the first announcement is regarding your final examination. I think the program coordinator have posted the information in the our ISM website, so you can check the latest information. In fact, I have told you before that it's on the 9th of the February from 3 to 6 p.m. Okay, so we are using the spectrum. It's similar to what you have done for your test 1 and the test 2. Okay, I will upload the question in the spectrum. Then you download the question, you answer, you scan your solution, then you upload it back. So the duration of the exam is 3 hours. Okay. So this one is regarding the exam methods. But if you have want to know about the further information about this semester, especially those students who are taking the projects or the progress presentation and the project presentation, I believe that they have updated the information here. So make sure that you check it, all the information in our ISM website, or you can receive, sometimes they will send you the email. Okay, so this one is the first announcement. About the second announcement is you have gone through your test 1 and the test 2. Okay, so refer to your test 1. I have announced the results. For the test 2, I will announce it next week. Okay, after I finish the marking. Okay, I will announce and then I will discuss with you all for the test 2 next week. Okay, then another thing is last week I have mentioned to you all is about the assignment. So this one is a group assignment. If you're unable to contact your friends, you can use the WhatsApp group so that all of you can gather together under the same groups. Okay, I have assigned the grouping here. Okay, it's according to the, actually I saw it according to a magic number, so you can be checked among your friends. Okay. If you're unable to find them, then you can be post the information in the WhatsApp group so that you can you all know each other. Okay. So this one is the information for the assignment. So assignment, the due date is next week. I will give you until the next Friday. Okay. Yeah. So this one is contribute for the final examination. Contribute for the continuous assessment is 10%. Where else the test 1 and test 2, each one will contribute to the 20%. Okay. In fact, I have mentioned all these things in the cost information, current cost information, and then your final examination is 50%. Okay. So this one is an announcement I wish to inform you all. Okay. So today we will go through the last chapter. Okay, we will go through the last chapter. This chapter also is a I think not the very long chapter. Yeah, I have given you the notes. Okay, I have given you the notes with some results, but some of the discussion maybe I will discuss it here. Okay. So the last one, the last chapter is about the robust design. So robust design, in fact, is developed by the Taguchi. It's by the person is called the Taguchi. So this one is normally you can see they call as a Taguchi method. Okay. So the robust design is essential a principle that emphasize proper choice of level of controllable factors in the system, or they call as a parameters. Okay, so in this one, if you still remember previously you have studied before, we have how many factors in the factorial design. You are studying the factors, so you want to know that under the factor A you have A levels, factor B you have a B levels. So you want to find out which level is give you the optimal solution, or is there any significant difference for the factors A's among all the levels and so on. Okay, so similar to the here also, we also emphasize on those of the correct choice of the controllable factors in the system. Okay, in this chapter, we call it as a controllable factors. Okay, it's similar to what you have practiced it before, where you have different levels of the factors. So the objective of this design actually is include, the first one is to ensure the mean of the response output is at the desirable level or target. So it means that you want to know what is the objective. if you study the factor in the factorial before, so you want to find out what is the response give you the highest mean, or you want to have a lowest mean, or you want to the mean is close to the target value. So the objective of the robust design will be the first one is to ensure that the mean of the output is at the desirable level or the target. Okay, so means that you set the certain target, they want to close to the target, or you want to have a maximum, or you want to have a minimum. So later on, we have a different measure to measure it out. Instead of using the mean, we have a certain measurement to measure it. Okay. The second one is to ensure the variability around the target value is as small as possible. So the first one is to ensure that the mean will be close it out. The second one is a variability, is talking about the variance or the standard deviation. The variation of the data around the target values must be as small as possible, so they don't have the much variation. Okay. So this one is the objective of the robust design. Okay. So in the robust design problem, the focus is usually one of the one or more following. The first one is give you an example, designing a system that are insensitive to the environment factor that can affect the performance once the system is deployed in the field. An example is the development of the exterior paint that should exhibit long life when exposed to the variety of the weather condition. Because the weather conditions are not entirely predictable and certainly not constant. So the product formulators want the paints to be robust against or withstand a wide range of the temperature, humidity, and the precipitation factors that affect the wear and the finish of the paint. Okay, so this one is one of the example. The second one will be design the product. Instead of the system, they design the product that are insensitive to the variability transmitted by the component of the system. Means that the variation, they are not affected. Okay. An example is designing an electronic amplifier so that the output weightage is as close as possible to the desirable target, regardless of the variability in the electrical parameter of the transmitter, resistor, and so on of the components of the system. Okay. So for the second one, we will want to have the insensitivity to variability, and then at the same time, we want the output will be as close to the as close as possible to the desirable target. The third one, designing of the process, so that the manufactured product will be as close as possible to the target specification, even though some process variables such as temperature or the raw material property are impossible to control precisely. Okay, so this one is the third one. After that, the following one will be determining the operating condition for a process, okay, so that the critical process characteristics are as close as possible to the desired target values, and the variability around the target is minimized. Okay, so all these things, as you can see out, they all will be close to the target value. Okay, and then they want to have the variability must be as small as possible. Okay, so here are some examples of the following one. Okay, then the following one will be the an important aspect of the Taguchi approach was his notion that certain type of the variable cause variability in the important system response variable. So we refer this type of the variable as a noise variable or uncontrollable variable. So just now I have mentioned that we have a controllable variables. Then this one is another variable is called the noise variable. So in the Taguchi approach, they consist of the two type of the factors. Okay, as you can see from this diagram, the input then go to the process, then you come out your output. Okay, so you have some factors will be considered as a controllable. The second one, the jack here, will be considered as an uncontrollable factors. Okay, it's not really they cannot be controlled, but it's very hard for you to control it. Okay, so these are the two controller and control, then towards the output of the here. Okay, so in general, the experiment will be used to study the performance of process or system. So this is a diagram to represent it out. Okay, where your y is referred to the response. Your y will become the response variables, and then the x here will become your controllable factors. The z here is considered as uncontrollable factors. Okay. So if you run the process here, then of course the objective of the experiment may consist of the which variable are most influenced on the response y. What you have studied before in the factorial design or one factor, you also want to see that which factor is considered significant. Okay, so you want to know they have the significance to the response. The second one is determine where the set of the inferential x so that the y are almost near, always near to the desirable nominal values. Okay, so we want to know that what set the inference of the x. The third one, determine where to set the inference of x so that the variability is in y is a small. So the variability we're talking about the variation of the data will be variation will be small. Okay. Then after that, the following one, determining where to set the inferential x so that the effect of the uncontrollable variable will be minimized. Okay. So this one is here will be followed by the following page here. As you can see from the foregoing discussion, the experimenter always involve the several factors. So the objective of the experimenter is to determine the inference that this factor have on the output system output response of the system. So the general approach to planning and conducting the experiment is called the strategy of experimentation. So the experimenter can use several strategies. Okay. So yeah, they can be used as several strategy. Of course, I do not list down all the strategy here. You can be find out for all the strategy from the books here. Okay. So refer to the just now, you have controllable variables. Then another one is called the uncontrollable variables, or they call as a noise variables, or they call as a noise factors. So the noise factors are often the function of the environmental condition, such as the temperature or the relative humidity. So this type of the noise variables is hardly for you to control. Or some example of the uncontrollable or the noise factors will be the property of the raw material that varies from the batch to the batch over the time in the process. So if you still remember last time you have seen before the blocking, you have a Nelson factors. Yeah. So this one is quite similar the structure with the Nelson factors where is they will affect your results. So they may be the process variables that is difficult to control or to keep at the specific target. Okay. So in some cases, they may be involved the way the customer handle or uses the product. So these are the three. In fact, these are the three examples: the environmental condition, the raw materials, the variables where they are. The following one will be the customer handle the users of the product. These are some example of the noise factors. Okay. So the either you call as a noise factors or you call it as an uncontrollable factors or you can call it as a noise variables also possible. Okay. So noise variables may often be controlled at the research or the development levels, but they cannot be controlled at the production or the product use level. Okay. So the following one of the here regarding here and integrate parts of the robust parameter design. Problem is identifying the controllable variable and the noise variable that affect the process or the product performance, and then finding the setting for the controllable variables that minimize the variability transmitted from the noise variables. So strictly speaking, it means that the most robust parameter design is the one is insensitive to the changes of the noise variables. Okay, so later on I will show you that they want to minimize the variability across the dose of the transmitted by the noise variable. So later on I can show you the the following part will show you the cross array design, such that you can see that the arrangement of the controllable variable and the uncontrollable variables, then we will expect that they have minimized the variability transmitted from the noise variable. Okay. So first thing you need to clearly know that in the robust parameter design, or they call as a robust design. Okay, I use the short form as the robust design, or you call it as a robust parameter design. They are the same. Okay, where you have two different factors. One of them is called the controllable variables. Another one is called the noise variables or uncontrollable variables. Then we will do it in the way of you present it in the way such that they can be analyzed in the following one is called cross array design. Okay, so this one will lead you to the following parts here. So under the cross to analyze for the just now the controllable and the uncontrollable variables, so we have a cross array design here, where the notation of cross array design consists of the controllable factors and uncontrollable factors. So the controllable factors we call it as an inner array, okay, because it's cross array here. After that, you have an outer array here is considered as uncontrollable factors. Okay. So here is one of the example of the 2 power of 4 minus 1 factorial, the fractional factorial design. Okay, so you have 4 factors here. You only run for the 2 power of 4 minus 1 is a fractional factorial design, 1/2 of the fractional factorial design. So 2 power of 3, you have all together is 8 treatment combination here. Okay, so the notation of the x here is given as the controllable factor, or I use the notation as the x. Okay, I call it as the xi here. Okay, for the uncontrollable variables, we have 2 power of 3 minus 1. Okay, for the 2 power of 3 minus 1, it means that you have a 1/2 of the fractional design. So the uncontrollable variable, we use a notation as a zi. Okay, so here will be your uncontrollable factors. This one will be your control factors. So as you can see out, under the first treatment combination of 4 from the negative, 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 or at the low level, you run the first one. Okay, under the negative one, you have a negative, 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 you get the first observation. Under the first one also, you can have a negative, negative, positive, you get the y2. Okay, so this one is a meaning of this diagram. And then for the last one, is under the all at the high level is a plus, then you can have a minus, 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 is a observation number 29, after that and so on. So altogether, you have 32 observation. How do you count the 32 observation? This one, you have a 2 power of 4 minus 1, you have 8 of them. Because it's a cross array. So you cross with another one. For this one, the uncontrollable variables, you have a 2 power of 3 minus 1, you have a 4. Okay, 2 power 2 is a 4. So 8 times is equal to 32 observation. So therefore, you have a 32 observation here. Okay, so from this diagram, maybe you cannot see it clearly. Okay, how this one is arranged. Then here will be show you another example. Yeah, this one will be what they call as an inner array will be here. So you study is 4 factors. These 4 factors will be the ABCD. Okay, ABCD. You have 4 factors here. And then for the outer array, where this one is called the uncontrollable variables, you have 3 factors here. Then these are the combination of the factors here. They may not be run completely. They can be run the fractional, or they can run completely also possible. Like this one have a 3 factors. Each factor consists of the 2 levels. So by right, they should have a 2 power of 3 factors here. So it's equal to 8. So you have a 1, 2, 3, 4, 5, 6, 7, 8. So therefore, this one is run completely. But however, for this thing, it's only run 9 of them only. Okay, so this one is what they have called the analyze of the cross array design. You have an inner array, you have an outer array. So your table will be given as a following one. Okay, so just now they say that for the each of the treatment combination, we will expect that the transmit by the here, they are almost close to each other. Okay, so we minimize the variability transmitted from the noise variable. So we expect that the variability transmitted across here, across all these things, they will almost is minimize the variability. Okay, so this one is how the robust parameter design will do. Okay, so these are the result. Here it show you the result. Of course, under this particular treatment combination with this particular treatment combination, you obtain the first results. And then you from here the second treatment combination with this combination, you obtain the following experiment. Okay, so under this cross array design here, we will expect that we want to looking for what are the factors here, A, B, C, D, which of the factors will be produce the largest mean or the smallest mean, or the value will close to the target value. Okay. So this one is because this thing is a controllable variable, so we are interested on the controllable variables. Okay. So their approach will be different from the ANOVA types. In the ANOVA types, you run the ANOVA table and then you try to test it whether it's significant different or no significant different. But in this approach will be different. They just use the mean and variant to come out the conclusion of the whether which levels under the certain factor, which level if you wish to have a maximum, then which level will give you a maximum, which level will give you the minimum. Okay. So to analyze for this particular table here, okay, for this type of the result here, how we want to do that? So first thing you must make sure that your inner array must be your controllable variables. The outer array will be your uncontrollable variables, and then you run the experiment, you obtain the following results. Okay. So here are some the main thing of this chapter. Okay, of course in the robust design they have a lot of controversy about their techniques used. Okay, I do not discuss in detail about the techniques, why they have a controversy. I do not mention it clearly. Okay, of course you can be looking at books and then you go to Google to check it out. Okay, so under the Taguchi methods, they suggest that one may summarize the observation in each of the outer array with a summary statistic that provide the information about the mean and variance. Okay, so this summary statistic is called the signal to the noise ratio. Okay, so how is we will use the signal to noise ratio to decide what are the objective we're going to achieve, or what is the goal you're going to achieve. Okay, and the statistical analysis is done using the SNR on the response variable. So this whole thing is a response variable, your Y. Okay, the whole thing is your Y. Okay, so in fact they have a different type of the SNR. So I will show you just these 3 of them. Okay, the choice of the SNR will depends on the goal of the goal of the experiment, whether you want to have a minimum or maximum or the close to the target value. Okay, so the first one, if you wish to have minimize your response, this one I believe that you have seen before, minimization or maximization. You want to maximize your response or you want to minimize your response. Therefore, you're looking for the overall mean will be the smallest or the largest mean. Okay, so in the previous chapter, you have a few chapters you have learned it already. So in the following case, if you're using the different approach, the smaller the better. We want to have minimize the response. So to calculate the minimized response, this is a formula given here for the SNR here. For the smallest, is a minus 10 multiplied by log 10, the summation of the yi square divided by n. So you sum out all the yi square divided by n, then you take the log of them. Okay, so in the calculation of the SNR, the summation of the I equal to 1 implies that summation over the n response variable at the outer array point. So this one means that to calculate summation is actually the summation across here. Okay, all these things. Okay, for each one. Okay, for each of the inner array, then we calculate the summary for all the here. You consider the whole thing here, the summation here. So therefore, this one, if your n equal to 1, 2, 3, 4, 5, 6, 7, 8. In this case, is 8. So the n is referred to here. Okay, so this one is what I means by the summation of the I equal to 1, and it implies the summation of the n response values at the outer array point. So it's this part. Okay. So the yi is your observation. You just do the summation, then you can calculate the S and R for each one. So the values of the control variable are short that maximize the S and R. So you want to looking for the minimization, then we're using the following formula for the minimization. Okay, hold on, I reply what? Okay, I think somebody, today we should have a class, but somebody still ask me whether have a class or not. We have a class, yeah. Okay. So for the SNR, this one is if you're going to have a minimize of the problem, then this one is a formula for SNR you use. Okay. Then after you get the SNR, all these things, then which one you want to choose is we try to choose those of the values with the largest SNR. That one is your conclusion. Okay. So later on, I will show it to you here. So in the SNR of the smaller better, it means that in this case, if you form this diagram, so you have altogether is 9 different combination, then you should have 9 SNR. So therefore, if you want to have a minimize, then we from this data set, we calculate the first one, the SNR. The second one, we still calculate the SNR, and so on until the SNR last one. Altogether, you have 9 of the SNR. So from the SNR here, then we will find out which one will give you the maximized answer or minimize. Okay? But if you want to minimize your response, then you're using this formula. But anyway, to decide which one is your answer, then we need to find the maximize of the SNR. Okay? The second one, the larger, the better. Means that you want to have the maximize your response. You want to maximize your response. So if you want to maximize your response, so this is a formula you use. The difference in between these two is just take the reciprocal of the y square here. Okay, so you just take the summation of the 1 divided by y square here, and then you just calculate according to using the following formula. Then again, the value of the control variable are short, that the maximize the SNR. So means that later on you calculate all the SNR, which one is your chosen control variable under which level, you need to choose the largest SNR. Okay. The third one will be the target is the best. Means that some of the experiment, we want to close to the target value. So for example, if you are producing the bearing of the bearing, you have an inner bearing and outer bearing. Then of course, we want to close, the mean must be close. It's not say that the mean is smaller. Because the bearing, if your size is not matched, you cannot be entered. Okay, cannot match two bearing, inner and outer. So therefore, they must be go to the close to the target value the best. Okay. So if you're going to have a close to the target value, then this one is the experimental will be have here close to the particular target value. So the SNR here using this formula, where instead of using the observation, we're using the variant. Okay, S square is just a variant of the data. Okay, so you calculate the variance of the data, then against the control variable are sort that the maximize the SNR. So means that after you get all the SNR, then we look for the maximum of the SNR later on. Okay. So in this chapter, these are the three important criteria for you to do the decision of the which variables is considered. Okay. So I will give you the one of the examples here, and in fact I have included two examples here. Okay, yeah, the two examples here. Yeah, I have included sorry, I have included just one example here. Okay, the first one will be here. So this one is an experiment here. This one is a factor levels here. They consist of each of the factor. They consist of the two levels. They have a low level. There's a high levels. Okay, so they have a low level and a high level here. So this one also the second factor will be have a low level and a high level and so on. So altogether they consider is a 6 factors here. Okay, so these are the factors they call as a controllable variables. They want to know that under this one which level will perform better. Okay, if they're going to have the minimization or the maximization. Okay. So in this example, first example here, it actually they are going to determine over here the experiment is designed to determine the condition that give the minimum number of the shoulder defects per million joints. So they are actually looking for the minimization. Okay, they are looking for the minimum. Okay, minimization problem is not the maximization problem. Okay, so these are the factors A and the E with the each factor they consist of the two levels. So there are also the three noise factors that are difficult to control in the process. Okay. So even though they are difficult to control, but they still try to control it using another form. It's called they try to control it. Okay, in the two different levels. Okay, of course they can have different techniques of doing it. So you can see that it is known that the control of temperature within the 5 and the control of the conveyor speed is within the 0.2 feet per minute. So these are the things is they cannot be measured exactly of the noise variables. So therefore they control in the certain range of them. Okay. So these are the things is you can read through the details. They are called uncontrollable variables, where this thing is very hard to control. It's not say that they totally cannot control. It just say that they are very hard for them to do the control. Okay. So this thing is an uncontrollable variable. They consider F, G, and H. So therefore, we can present our the form or the design in the cross array design, where you have A under the E, 5 factor of the inner array, and then you have 3 factors of the outer array. Okay, so these are the diagram you can see here. Okay, so the inner array consists of the A under the E, and the outer array they only have this here F under the G. So if you consider here, they should be have a 2 power of this one. It should be have a 2 power of 3, but because of they only want to run for the fractional, so it's a 2 power of 3 minus 1. It's only 4 different combination. Okay, similar to here, they consist of the 5 factor, so they should be have a 2 power of 5, but they only run here is 8 of them, so it's a minus by 2. Actually, this one is a 1/4, so it's 2 power of 3. Okay, so they run for the the factor A here is just a fractional. For the this part also they run for the fractional of the 4 only. Okay, of course you can run all, but if you run all of them, then you can have many of the different levels combination. Then if you also can run the full set, then you have a 2 power of 5 is a 32 combination. Okay, so in this case, we have only here is 8 of them. Okay, 2 power of 3 multiplied by 2 power of 2. So you have 8 times 4, you have 32 observation. Okay, so you have a 2 power is 8. Here is 8 times 4. Yeah, it's 8 times 4 32. So you have a 2, 4, 6, 8. 8 times 4, you get 32 observation here. Okay, so here are the 32 observation. Okay, so if you don't want to run the fractional, you want to run more, then of course you need to run many experiments. Then you only can decide which one. Okay. So over here, as the just now from the question itself, we want to know that is the minimum. Okay, the problem in this scenario is want to find the minimization. So if you are looking for the minimization, then of course, when we calculate the signal to the noise ratio, we are using the SNR of the minimization. Okay. So in this diagram, we are using the SNR for the smallest will be equal to the minus 10 log 10. After that, you have a summation of them, summation yi square divided by n. Okay, so you have a SNR because you have all together is a 8 treatment combination of the under the control variables. So suppose you have all together is 8 values of the SNR. Okay, so maybe I can show you the first one. So this one is the first one. So the first one of the SNR will be equal to minus log 10 log 10. Okay, you sum it out, then it should be 194 square plus 197 square. Okay, so if you calculate this thing, okay, so you will get your answer with negative 46.75. Okay, so this one will equivalent to the first value of here. Okay, so you have all the S and R value. Okay, you have all the S and R values here. So based on the S and R value here, then we are going to decide which one will give you the largest or the smallest S and R here. Okay, so now I already show you how to calculate the S and R value. Okay. So after you know how to draw the S and R values, all the S and R value you have found it out. Okay. So now we are going to find out how we want to draw for the following plots and then to decide which one will be the levels you are consider. Over here, you have many different levels. You have a low level, you have a high level for the each factors. So from the each factor of the factor A and factor B, factor A, you want to decide for the low level or the high levels, or you want to have a factor B, factor C, and so on. Okay. So we will base on the idea of the SNR here. Okay, but before we go for the SNR, let me introduce for you the bottom, the graph first, the mean first. Okay, let's say we are doing the plotting of the mean. So first thing, we will plot the temperature. Temperature is referred to your factor of the A, the first factor of the A here. Okay, so under the first factor, or this one is a factor A. The speed will be the factor B. This one density will be C. And then this one will be the D. This one will be E. Okay, so there are different factors. For each factor, you consist of the 2 levels here. So if you want to calculate the mean or the lowest of the mean here, Okay, we calculate the mean under the low level, then you can get the first mean here. We can calculate the second mean here at the high level, then we get the average value of here. So how to get the mean here? Of course, you just refer back to your diagram just now. Okay, this one is a factor A at the positive, the high level. This one is a low level. So if they are low level, you just take the average value of the overall. Okay, you just take the average value of them. Okay, you just take the average value of all this data, then you can get your mean value. Okay, so for the A at the high level, you just take the average value. It's not the S and R yet, because now I refer to the mean. Okay, I do the mean first. So you can see that this one is the mean at the low level, this one is the mean at the high level. So similarly, for the factor B, the mean for the low level is this value. The mean for the high level is this value, and so on. Okay, so this one is referred to the factor A. If last time you test the ANOVA, you can see that this one is a big difference. So it's the since that there is a significant difference from the low level to high level. Whereas for the factor B, you are not uncertain. Previously, you need to conduct the hypothesis test to test whether there is a significant difference from the factor B or not. For the factor C, it seems that they have a big difference. For the factor D, it looks like they are almost the same. For the factor C, also there seems that it's not very much different. But in the Taguchi approach that here, we just based on the SNR to decide for the each factor. All these factors we consider they are the important. But we want to know that they want to operate under the low level or the high level. Okay, so this one is from the mean here, because just now the objective of the study, they want to have a minimization. So basically, we may consider the minimization. We will consider the following one. Choose the temperature A at the high level, the speed at the low level, the density at the low level, because we are wish to get the minimization problem. For this one, from the graph here is unable to see clearly, then maybe they are almost the same. For this thing, we can consider this one, okay, at a low level. For this one, they are almost the same. Okay, so these are the roughly, if you plot the mean plot, this one is what you consider. You may operate the factor A at the high level, factor B at the low level, factor C at the low level, and then the factor D, any levels also possible, and then the factor E at the low level. So this one will be expected if you're using the mean. Okay. However, in this here, we have learned how to use the SNR here. So therefore, we go to the SNR. Just now we have calculated the SNR here. So over here, we can plot the SNR here. So to calculate the SNR here, okay, okay, so to get the SNR or to get the SNR here, you can see that this one is also the factor A, this one is the factor B, C, D, E. So under the factor A here, the low level of the SNR, if we consider the SNR, so how to get this value of the low value of SNR? Because you see under the factor A, you consider low level and high level. So means that under the low level here, you use these four. Take the average value of these four. For the high level here, you take the average value of these four. So these two, this one, and this one, they will go to this one, the first one, not merge them together. What I mean is you get the average value of here, you get the average value of the here under the factor A, the high level and low level, then you can get the S and L value, this one and this one. Okay, so you can be checking out. Okay, so this one will be your low level, this one will be your high level of the SNR. Similarly, for the factor B, you have a low level and high level. So because you are plotting the SNR graph, so therefore you go to the factor B. Factor B, you have here is a positive. So you just refer to these two SNR and another two SNR. These four, you join them together to take the average value for the high level, and then for negative side, you also take these four values, take the average value, then you can be obtain the low and the high value. Similarly, you can be do for the following one. Okay, you can be try to calculate out. Of course, the diagram cannot be perfectly show you, but you can see that your value when you calculate the average, they are somewhere around here one. Okay, so from here, from this diagram here, from the SNR diagram, then we will decide. Because if we want to have a minimization problem, of course, we already use the formula of the SNR minimization problem. But when you want to decide which one I should be choose, against, I have mentioned it before, all these things will be decided by the maximize. Okay, all these things will be the maximize of the maximize of your SNR. All these three techniques here, we choose the answer will based on the maximize the SNR. Okay, that one will lead to your answer. Okay, of course, you want to have a minimization problem. You already use a minimization formula. Then you want to decide which level you consider. Then you choose the maximize of the SNR. Similarly, for the all these three techniques is maximize. So therefore, in this diagram here, we will decide to choose this one is the SNR. Okay, after I get the average value of all the SNR here, so we choose for the maximum here, here, here. This one will be clearly, you can see clearly, this one will be here. So therefore, this one will be A at the low level, the B at the high level, the C at the low level, and then the D at the positive level, the E at the low level. So these are the levels you consider if you want to minimization of your problem. The technique will be quite simple. Therefore, they get a lot of the control we'll see as compared to the ANOVA. Okay, so this one is how do you do for the SNR? Okay, given the SNR, and then you perform it, you calculate, then you decide which one will be considered. So these are the combination you consider.
Sorry, doctor.
Hello. Yes.
Yeah, sorry, doctor.
Hello.
I want to ask, should the A be the high level?
Oh, sorry. Yeah. A at the high level is plus, correct? Because it's a high. Yeah, thank you. A plus,
okay.
plus, minus, plus, and the minus, correct? Yeah, correct. It's a plus. Yeah.
So we don't take the combination from the table. We take it from this chart.
Yeah, you go from this chart. Because
Okay.
from this, from this chart, after you calculate this thing, we need to analyze it according to the low level and high level. Therefore, once you calculate this thing, you use this one to provide their mean value for the low level and high level. Then we want to decide which one will give you the maximum of the SNR. Okay.
Okay.
Yeah. So this one is how do you decide it out for the first graph of here. Okay. So of course here. Yeah.
Sorry, doctor.
Yeah.
I want to ask if we choose the maximum of SNR, right? Does that mean we are choosing the maximum output as well?
No, because you see that all these things, we want to choose the minimization problem. We're already using the following formula. We want to have a maximization problem. We already change the formula to the 1 divided by. So finally, all these three techniques, we will consider those of them give you the largest SNR. It's not related to this thing anymore.
Oh,
yeah,
okay.
Because
so,
your formula is different.
Oh, okay. So regardless of whether are we trying to minimize or maximize, as when we
Yes.
got the SNR, then we have to maximize the SNR, is it?
Yes. Actually, they are
Okay.
related to the loss function one. Okay, only I don't tell in detail only about it. Yeah, all these things is a maximize of the SNR regardless what you have these three. Okay.
Oh, okay. Okay, thank you.
Yeah.
Excuse me. Yeah. So the last two charts.
Yeah.
Is the answer supposed to
Last two chart,
coincide?
which chart?
So the last two, one is SNR, and then the other one you plotted the mean.
Mean.
Yeah.
Yes.
Is it supposed to give you the same answer?
Suppose we the same answer, but you can see that this thing you are very hard for you to decide. Because this one is only take care about the mean. But if you consider the SNR here, they will be using the based on the loss function. Therefore, they can be see clearly about what is the difference of this thing.
Oh, so it's different criteria. Okay.
Yeah. So you can see more clearly which one you select. Suppose both of them must be coincident. Must be consistent. You using the mean or using this one, they should be consistent one.
But since if we follow Taguchi's method, then we just use the SNR lah.
But you need to plot this thing so that, because if you're talking about SNR, people may not be know SNR. So therefore, if you're talking about the average value, people can see clearly what is your year of under here, what is the value of the here. So basically, we'll plot two together. If you just produce the SNR, people may ask you what is the SNR.
Yeah, because in this case, it's not the same, right?
Which one is not the same?
Your answer.
The answer for this thing, you can see that this one you choose the A positive. This one B negative. This one C negative. Correct. Then this one is will be the do not know, because they are almost the same. For this one, we can be D, we not sure. Then the E, we will have this one is a negative value. Okay, so the answer here may be the B is at the plus side. They should be at this one. So based on the S and R will be your decision based on the Taguchi method. But of course, when you present it out, you can be present both of them so that the people will know that what is the value of here in the real values.
Okay, thanks.
Yeah, correct. You say it's correct. It's no consistent at here, and then some more. This one also we do not know unless we clearly get the mean out. Okay. So this one is the first. Actually is this one. Okay. Then after that you here. So from the graph here, we are clearly that the suggested condition will be the first one will be the temperature. We look for the high level of the temperature, and then the flux density. The flux density there, we want to consider is a low level of the flux density is 0.9. Okay, 510 is actually refer to the here. 510 at the high level here. Okay, then after that, the flux density they suggest is a 0.9. This one, it should be not the 9, it should be the 0.9. Oh, I think it's a fault from the books. Okay, they will suggest this one. Then after that, the wave height they consider as a low level here. Okay, so these three are here. Why they do not survey of the B and the D here? Because from the B and the D here, you can see that they are almost quite flat. This one also is almost quite flat. Even though you are looking at the mean here, there are since that if you test the hypothesis, you may get the answer is not significant different, especially this one. Therefore, they do not consider these two in the study. Okay, this one is what we learn the statistic. We use directly the statistic technique to do that. Okay, but in the here they never test it. Okay, they never test the hypothesis whether there is a significant difference of these two or not. Okay, if they know significant difference, then we can give out it. Okay, besides from all these values here, we find the experimental values of what they get it out. The company also may consider other factors, consider as a cost factors, where they change their mind to use a different levels also possible. Even though, like this example here, I say that is we have to consider the maximum of the SNR, we will choose this value. But if it has the mean is no significant difference, so we can give out the speed. Okay. But anyway, if let's say the company think that using the high level, they do not have a very much significant difference, so they will prefer to choose the low level also possible due to the cost. Okay, then they can consider here. But in our here, the cost here, we need to have a certain benchmark. All this cost is when you run in the production, then you only know whether which one you want to give out. Okay. Yeah, you want to give out any information. Okay. So now we just based on the maximum of the SNR, then we just select which factor you consider. Okay. So in your test, I also will do that. We just based on the standard benchmark. Okay, the maximum one, then we choose it. Okay, unless I state other condition there, I say that if this graph is since that this graph, I will state that the D will since that is no significant difference, so the experimenter will be decide to give out this information. So you will choose the maximum SNR based on the ABC and the E only. Okay. Otherwise, you just choose which one is maximize your SNR. Okay. So this one is your, from this example, they only consider 3, okay? Because of the just now I have mentioned, they can consider other factors, then they come out the conclusion. Okay, so this one is the first example. Okay, it's a first example. I have another example, but because of that example will be deal with the 3 power of k factorial design. Therefore, I do not put it here because what your the cost for this course, if we only study until the 2 power of k factorial design. Okay, we only go for the 2 power of k factorial design. Therefore, I do not go until the 3 power of k factorial design. Okay, so this one is the last chapters of the robust design. It's I think it's a bit very short about for this part. Okay. So of course, under the robust design, if you have a books one, you also can be see out. But for your information, in the textbook, the robust design will be a bit different from what I given it to you, because in the textbook you are unable to find out the SNR formula. So the formula of all these SNR, I will get it from the other books. Okay. Then furthermore, for your textbook one, the SNR actually they try to relate to the regression model. Okay, they try to relate it to the regression model of the mean and the variance model. Okay, so I believe that this one is that's all for this part of the SNR here. Okay, or the robust design under this part. Okay. Okay. Any of you still have a question? Okay, you can be read through it. Then yeah, we can decide it here.
Professor, what textbook are you referring to for the?
No, actually, the 2 textbook I have given this one, the course information. Not this one. I'm using this one. This one is our main reference, but because of here the limited information of this one, especially for robust design, I'm using this one. This one.
Okay.
The second one.
Okay, thanks.
Yeah. Oh, the third one, the third, fourth, and the fifth one. For this one, they also using the design or experimental. The number 4 one is more to the more to the mathematical type. There are less examples for the 4th books. The 5th book also is they are robust design one. Yeah, so here are a few of the textbook here, but I think that these two are the easiest to understand because they provide the examples and then you are easy to see how to apply the formulas. Yeah. Okay. So this one it should be the last one for the robust design. Okay, this chapter is very short. Okay. Yeah. So yeah, I think that's all for this one, the lecture. Another thing is I need to inform you, I have updated the tutorial 8 with the solution for the 11.8, where in fact, the solution is I took it from the books where I do it, they cannot get the answer from the, I think they have modified the data set, but they don't update their solution. Therefore, the answer is not the answer is incorrect. Okay, so I have updated the new version of the 11.8, the solution for the 11.8. This one is I do it using the Minitab. Okay, and then for the 11.10 also, in fact the answer is correct. I just replace the solution with the from the Minitab only. Okay, but the answer in fact before that is also correct. Okay. So the next one I want to go through with you is about the, okay, so before I go through this tutorial, so make sure that when I for the last chapter definitely will come out in your final exam, because the final exam will be consist of the all. Okay, they consist of the all from the chapter from the beginning until the end. Okay, until the robust design here. And then because of robust design, the important thing is just the SNR to decide which level of them using the Taguchi approach instead of using the analysis of variance, what we have done it before. Just a different approach, okay, to decide which level is what you're going to use. So therefore, I believe that the last chapter will be the, of course, the last chapter cannot be standalone, the one particular question. They are part of your, for the final exams. Okay, but if the last chapter will ask you, we ask the question from the last chapter, we will ask you is all related to the SNR. Just now I show it to you. Okay, so the question will be quite direct for the, especially from the last chapter. The rest of the chapter you need to practice. Okay, so make sure that you are aware about the what happening about the how to calculate the sum or square, how to calculate the effects. Okay. So for the, yeah, any of you okay, this one I think this tutorial I have given you before, is it? Okay, so they consist of the four question here. Okay, they consist of the 4 question here. But for the question 1 and question 2, this one is about the method of the signal action or method of the signal decision, or the path of the signal action or the path of the signal decision. So that one is this one is a tutorial 8.1. The for first 2 questions will be related to the response surface. Then of course I will not ask you to draw those of the response surface diagram or this thing, okay, because you do not have any software to do the drawing. So therefore I do not ask any of the drawing. Okay. So in the tutorial 8, they consist of the 4 questions. The first 2 questions, I will ask you to check whether this one is fall in the path of the signal action, whether they fall in the path of the signal action or no. The first thing. After that, the following 2 questions, I will ask you to run the fit for the second order model. So if you're going to fit for the second order model, that one will related to the center composite design. The CCD. What we have learned it before is called the central composite design. So that one will fit for the second order model. So your second order model will be involve the regression analysis. Okay, so that one is before that I have introduced for you what is a regression analysis, and then how are we going to find the parameter estimate of the regression analysis. Okay, so in your question for the 11.2, any of you have a difficulty to get the 11.2? Okay. So in this chapter, in the response surface methodology chapter also, we also will face our exam question will be also quite direct. Is one of the possible one of the reason is because you cannot use the real data, because let me open it. Let me recall back what you have in the response surface here. Under the method of the signal action here, before that, we are moving the direction then to the path and then reach the optimal solution here. And then after that, we rerun the analysis under the optimal under the reach region so that we can obtain the optimal solution. So this one is last time what we have given to you. Okay. In the previous example where we have run the experiment and then we get the equation. And then we use the method of the signal action to locate the, let me show it to you. We move the direction. Let me see. Yeah, we move the direction, we move it, then we try to locate the optimal solution here. But every time you move your step, you need to have a new value of the response. Okay, so because we are not running the experiment, we know the techniques, but once we have a data, we only can do it one by one from here. Okay, so once you locate for this particular optimal at this part, then we still need to run the experiment under this particular section. Okay, so we rerun the experiment under this one to look at it whether the second order is important or no to fit your equation. So when you go through the tutorial question, because we do not have a data, so therefore we will just study on the technique itself. How we want to apply the techniques is important here. Okay, even though in your final exam, I will give you this type of the scenario, then ask you to given you the equation and then just ask you to find out whether they are in the path or is it their solution is a maximum or minimum only. I do not ask you to reanalyze the whole thing similar to the ANOVA. You form the ANOVA table from the beginning until the end. Okay, so when we start with the response surface and the robust design, these two chapters, the question will be quite standard. It's not deal with very much calculation as compared with the previous one. Okay, ANOVA table. But the previous one, even though you deal with a lot of the calculation, but I try to minimize your calculation by giving you more information. Okay. So this one is here. This one is the first example. Okay, I will explain for you the first one. Then you can be try to check it out whether you know the second question how to do or not. So this one is here. The region of experimentation for the three factors are. These are the three different factors. Okay, these are the three factors here where the range of the T1 and the T2 and the P is here is a range of the here. You study is the three factors and then they fall in the study in this range. Okay, then after they do run the experiment or ANOVA, then they found that the iteration effect is all not significant or this thing. They just do the ANOVA testing and so on. Finally, they come out with say that this is the model, is a fitted model. Okay, of course, this one is a fitted model. If you still remember, if this one is a 2 power of k factorial design, This one, the 30 is actually the average value. This one is a 5 is referred to the effects divided by 2. 2.5 also is the effects for the factor 2 divided by 2. 3.5 is the effects for the factor 3 divided by 2. Okay, so they get the following formula out. So about the previous one, we don't care, but if they given out the formula here, okay, given out this one, so now they ask you, is the point T1 is 85, T2 is 32, and the P is a 60 is on the path of the signal action. So is it they are in the direction of the path here? The path is means that yeah, in this direction or not? Or their point is not going to the same direction. Okay, so this one is what the question asks you, whether this point is really on the signal addition, signal the action or the signal descent. It depends on whether your minimization or maximization. Okay. So under here, first thing you from here you will know that if there are two levels here, 40 and 80, so you can be from the natural variable convert to the quoted variables. So the quoted variable for the x1 will be equal to t1 minus by 60. 60 is actually the average value of the okay, the average of these two is 120 divided 2 is a 60, and then the 20 here is the difference divided by 2. So it's a 80 minus a 40 divided by 2. So you get the 20. Okay, so make sure that you know how to do the conversion of here from the natural variables to the quoted variable. So after you want to confirm that whether your equation is correct or wrong, you just substitute back the T1. Okay, the T1, if you substitute back the 80, 80 minus 60 divided by 20, you get is 1. If you substitute 40, 40 minus 60 is a negative 20 divided by 20, you get minus 1. So therefore, the quoted variables will be the minus 1 and the positive 1. Then you are doing the conversion is correct. Okay. The similar thing will be the x2 will be given here, the x3 will be given here. Okay. Because this equation is a quoted variables, it's a x1, x2, x3 will be a quoted variable. Okay. So first thing, if you want to start your signal action or signal descent, of course, you need to set your starting point. Okay, you need to set your starting point. Then you need to have a step size is moving. So the setting of the starting point will be equal to delta t will equal to the 5. Delta t1 is equal to 5. Of course, you want to have a 10 also can. Okay, so it depends whether you want to how big your step size you want to move. Okay. After that, we will know that this one will be equal to the delta x1 will be equal to the delta t1 divided by the 20. Okay, delta x1 because x1 is equal to t1 minus 60 or 20. So therefore, delta x1 will equal to the delta of the t here. So the delta x1 is equal to delta t1 divided by 20. So the delta t1 is equal to 5 over 20. Therefore, you get 0.25 here. Okay, so this one is you want to know that what is your delta x t and the delta x1 delta x1. Okay, because you have a x1, x2, and x3. Okay, we denoted it as the delta x1, delta x2, and the delta x3. So since we know the delta t1 is equal to 5, so we can know the delta x1 is equal to 0.25. 0.25. Okay. Then after that, we also will know that your delta x2. Okay, the delta x2 will equal to the beta 2 hat divided by beta 1 hat. Okay, multiplied by delta x1 here. Okay, so your beta 2 is referred to the delta is referred to the here is a 2.5. Beta 1 is a for the x1 is a 5. Multiply just now you have the delta x1 is equal to 0.25. Okay, so you get your value is 0.125. Similarly, for the delta x3, also doing the similar way. Delta x3 will equal to beta 3 okay, beta 3 here is 3.5 over here is a 5 multiplied by what you have in the 0.25. So finally you get is 0.175. Okay, so you need to know what is your step size for the delta x1, delta x2, and delta x3. So we will start from here. The starting of the quoted is of course from the middle is a 0, 0, 0 because your quoted variable is from -1 to 1. So the middle is a 0, 0, 0. Okay, so your starting point of the natural variables will be here is a 60 because the middle will be the 60, 250, and the 35. How do you know 60? Because your range is from 40 to 80, so the middle is a 60. 200 to 300, the middle is 250. This one is the middle is a 70. 70 divided 2 is 35. Therefore, these three are the three. Okay. So the delta, just now we have decided the starting point of the T1 is equal to 5 here. So therefore, we have a 5 here. Okay. And then we already calculated the delta. X1 is a 0.25, point this one, and point here. So these are these three. Okay, so once we know all these things, we can calculate the 6.25 and the 2.625. How do we calculate it out? It just views the relationship of the natural variable here. So you have a delta x2 will equal to delta x2 is a t2, delta t2 divided by here is the 50. Okay, so from here we will know that is the delta x2 is 0. Okay, so you get the answer for the delta t2 6.25. Okay, similarly you want to get the delta x3 will equal to the this one is I call as a p, delta p divided by the total here is a 15.5. Okay, so therefore we have a delta p will equal to this one is a 15 multiplied 0.175. .625 is this one and this one, these two. Okay, so you already complete all the things. So after that, just plus a step. Origin plus the delta, the moving steps of here. So you get the second step. Then of course you can have a origin plus a 1 delta, origin plus a 2 delta, origin plus a 3 delta. Then until you run until the 5 delta and so on. So you calculate all the sets of here. Then because why they go so fast? In fact, when you have a origin plus a delta, then you can see that the natural will be at this direction. They are not very close. Then you can skip your step, go to the 5 delta, or you want to go for 6 delta. If you overshoot, then you go back. Suppose by right is you go for the origin plus 1 delta, origin plus 2 delta, plus 3 delta, then you only check whether this point is on the path or not. When they go until the 5 delta, 85 is your T1. But here is a 325 and the 60. So they are not in the correct direction. If they are in the correct path, then all these three values must be fall in the here. If they are the same value with this point, then they are in the correct direction. Okay, so this one is what the question 1 will ask you, whether this point is on the path or not. Okay, then of course, under this thing, if you run the experiment, under this condition, you run the experiment under the T1 is 65, under the T2 is 256, under the P is 37, then you get your Y. You under this condition, you get your response, and so on until you know which one will be the maximum. This one is similar to what you have here. in this example. But because we do not have a data, we do not run the experiment, therefore we do not have a data. Otherwise, you should be have under this particular here, you get the response. Under this one, you get another response. So therefore, you will see that the graph will be go for the maximum point. So you know that you locate the maximum will happen at here. Then you study it clearly. Okay. So this one is for the tutorial. I save it out first. Then I can upload this one for you. For those of you never do it, then you can try it out. Okay. Then you can go to see your second question will be the similar one. Okay. Can you follow this one? I don't know whether you have tried your tutorial or not. Okay. Okay. Never mind. I will. Yeah.
Can I use a different approach? So like, can I take the gradient of the function? Then I know that that's the path of steepest descent, and I can see that, you know, because 85, 325, and 60 is not that vector, then it's not on the path of steepest descent.
Yeah, you can be used any technique as long as you can show that your thing is not in the path, then I will consider one. Not necessary you need to using the following one to do the step by step.
Okay.
Okay. Even though in your solution, if sometimes you may have other techniques to do it. Okay. Then this one I leave it for you. You can check it out using the similar techniques, and then you check it out whether you understand about this thing or not. Okay. About this thing, it's called the fitting the model. Okay. The fitting the second order model. Second order model means that the equation consists of the y will be consist of the beta naught. If they are fitting the model, then if they study the two factor, then you have a x1. Okay, so you will involve the quadratic terms here. Of course, you have learned before, we can check whether the quadratic term is a significant or not significant to be included in the model. But since the question here, they already ask you to fit the second order, okay, they directly will ask you to fit the second order. So this one is a second order model. Okay, or you can see the name before that I call the CCD, Central Composite Design here. So when you want to fit the quadratic terms, you need the factorial point, number of the factorial point. You need the factorial point, means that you have a minus, plus, minus, plus, minus. You have a, this one is a 2 power of 2 factorial design. So you have minus, 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 plus, plus, minus, and plus, plus. So you have a number of factorial point is 4. Okay. Then because you are using only the n is equal to 1, only single observation, therefore you need the number of center point. Okay, you need to have a center point to estimate your MSE. So therefore this one 0, 0 is referred to the center point. This one is a NC will equal to 5 and F will equal to 4. Okay, so yeah, until here. Until here. So these are the point for the center point. These are the factorial point here. Then if you want to fitting for the quadratic effect here, then you need to have the oscillant here. So therefore, all these things will be equal to the oscillant here will be equal to the 4. Okay, I have mentioned it to you all. The oscillant here is get it from here. Let me see the diagram. Yeah, here. If you have a 2 power of k, 2 power of 2 factorial design, you have altogether is 4 oscillon here. So the 4 oscillon here is here it will be the oscillon here. You have a 4 point here. So the 4 point here is the alpha here. Okay, so the decision of alpha, they can have a different technique of the finding the decision, whether you have alpha is equal to number of factorial point, take the 1/4, or some of them they use the alpha equal to square root k. So in this example, they're using the here is a square root, here is a this one is 1.414 is actually they're using the oscillon is using the square root of the k will equal to square root of the 2 will equal to 1.414. Okay, so under the 1.140, the coded variable, you need to convert back to the natural variables. Then you will know what is the real natural variables. Then you run the experiment, you get the following results. So these are the results they run under all these treatment combination. Then they obtain all the results here. Okay, then we only can form the equation of the second order model. Okay, if without the oscillon here, you may not enough information to form the equation of the quadratic, the second order model. Okay, so how do you do the second order model? Okay, these are the results. I use regression. I use a regression analysis to obtain the result here. Okay, so maybe we stop for the while. I will tell you clearly about this thing. Okay. Yeah, so now is 7:31. We stop for a while, then we continue back. Okay, it's just have an additional of the small parts here only. Okay, yeah.
Professor, before we start, can I ask a question before we start later? Or
hello, can you repeat? I can't hear you.
Yeah, can I ask a question later before we start?
Can you want to ask me a question, or you want to ask me before that, is it?
Yeah, just I mean I can ask now also if you're okay with it.
Yeah, I'm okay, but some of them maybe if you want to yeah, you can ask those of you who want to leave first, then you can leave. Okay, then yeah, you can continue.
Because